Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, lesson 3, the motion of the moon, sun, and stars, motivating mathematics. All right, so this is kind of like your astronomy section in science when you were in 8th grade, astronomy. Classwork opening exercise, or opening, not really an exercise, just asking a couple of questions. Why does it look like the sun moves across the sky? Well, the reason it appears that the sun moves across the sky is because if I drew a circle, let's make it orange with a yellow line, okay? So here's the sun. There's the sun right there. And then if I do another circle and call that the Earth, like so, okay, the Earth rotates. For the Earth to go around the sun one full rotation like that takes 365 days and a quarter. And that's why we have leap year every 4 years. But it rotates as it's going around, and it rotates one full rotation every 24 hours because the Earth's circumference is approximately 24,000 miles at the equator, and it's rotating at about 1,000 miles an hour. Therefore, 24 hours, it'll go 24,000 miles around. And it keeps rotating as it goes around. So it's rotating counterclockwise. So it looks like the sun is rising in the east and setting in the west. And that's why it appears it moves across the sky. Now it says, is the sun moving or are you moving? Well, we're definitely moving. We go around the sun like this. We're definitely moving, and we're rotating as we're moving, okay? But I would say the sun is also moving because our entire solar system is moving, but the sun is at the center of our solar system, which is within the Milky Way galaxy, and the galaxy is moving. So in essence, the sun is moving, but with respect to our solar system, the sun is standing still in the center. And since it has the largest mass of our solar system, it is the center of the solar system, and everything is attracted to it because it's gravitational pull. All right, so in ancient Greek mythology, the god Helios was the personification of the sun. He rode across the sky every day in his chariot led by 4 horses. Why do your answers make it believable that in ancient times, people imagined the sun was pulled across the sky each day? Well, getting back to here, we now take what they thought the sun, we know the sun is a sphere going around a spherical sun, but back in the day, everybody thought the Earth was flat. So let me just do, why did that do that? Let me just do this. So let's everybody think that this is the Earth. Let's make it green. Okay. So here's the Earth's surface. Okay, so if I were here on the Earth, it appeared the sun was going like so across the sky. So that's why they believed it was being pulled. And since the Earth is flat, I don't know how they explained the fact that it came back around and did it again like this. Almost like a conveyor belt at the grocery store, maybe. So anyhow, maybe they thought the sun revolved around the Earth and the Earth was flat. So therefore the sun went down and underneath us and came back around, but the Earth was flat. That's why they thought that the sun was pulled across the sky every day. Okay, page 2. Before we get to that, I just want to explain this. It says to recall that the sun rises in the east and sets in the west. So its apparent motion in our model is counterclockwise. Indeed, this is where our notion of clockwise and counterclockwise comes from. If we are in the northern hemisphere, which we are, well, you might not be watching this video, But if you are above, north of the equator in the northern hemisphere, as the sun moves counterclockwise, shadows move clockwise. Thus, the shade on a sundial used to mark the passage of time moves in the opposite direction as the sun across the sky. So what they're saying is this, as the sun goes across the sky, the shadow of this dial goes this direction. Okay, and that's where the clockwise came from, because the original clocks were sundials. Okay, so this is why our clocks go clockwise, but the sun travels in a counterclockwise direction. Now, according to model, the movement of the sun, we measure the angle of elevation of the sun as it moves counterclockwise as shown. So counterclockwise is this way. So as the sun's going this way, our angle increases. So if it's at this, if the sun rises, it's at the horizon. It's at 0 degrees from our vision of our line of sight. As it goes up in the sky, the angle of elevation, as if you will, increases. So therefore that angle measure increases as we go counterclockwise. And that is why our counterclockwise direction is used in the Cartesian coordinate plane. And that leads us to this right here, the discussion. In mathematics, counterclockwise rotation is considered to be the positive direction of rotation. So counterclockwise is positive, which runs counter to our experience with a very common example of rotation, and that is the hands on a clock. So is there a connection between the counterclockwise motion being considered to be positive and the naming of the quadrants on a standard coordinate system? And the answer is yes. So since we're starting at the sun rising right here, as the sun rises, that's the first quarter of the day. You get to noon, and we are now in the afternoon, or the second quarter of the day, and then the sun sets, and then now it's nighttime, midnight, and then again, first thing in the morning. Okay. And that just keeps rotating around. With 24 divided by 4 is 6. So there are 6 hours in each quarter. So say that this is 6 a.m., this would be noon, this would be 6 p.m., this would be midnight, and then 6 a.m. again. So what does the circle's radius represent? Okay, the radius length r represents the distance between the center of the earth and the center of the sun. How has the motion of the sun influenced the development of mathematics? Okay, the naming of the quadrants and the idea of measuring rotations counterclockwise makes sense in terms of how we perceive the movement of stars and planets on Earth. So the next question says, how is measuring the height of the sun like measuring the Ferris wheel passenger car height in the previous lesson? Okay, well, both situations relate to a vertical distance to a measurement of rotation from an initial reference point. This page, we're going to start with a discussion. It says, in this section, we discuss the historical term used by the Ariabata the first in his astronomical work that led to trigonometry. Sanskrit names are spelled phonetically in the Roman alphabet. So Ariabata is pronounced Ariabata. So over here in the scaffolding, it says the words Ariabata and Jya and Koja can be chorally repeated by students. Okay, so it says to point to these terms on the image while asking students to repeat them out loud. So this, Jya, Koja. Okay, Jya, Koja. The best known work of the Indian scholar Ariabata the first, born in 476 CE, is the Aryabhataya, a compilation of mathematical and astronomical results that was not only used to support new developments in mathematics in India and Greece, but also provides us with a snapshot of what was known at that time. We're using his developments to model the position of the sun in the sky. Ariabata the first, spoke and wrote in the Sanskrit language. An arc of a circle together with the chord joining the ends of the arc are shaped like a bow and bowstring. So this red arc here is the arc they're talking about. And this green line here, and then continuing down and touching the circle again here, remember from last year, a line segment that has two endpoints on the edge of a circle is called a chord. Okay, and that's shaping what looks like a bow. Bowstring. The Sanskrit word for the bowstring is samastaja. Samastaja. Indian mathematicians often use the half chord Ardhaja or Ariabata. The first used the abbreviation Ja, pronounced Ja, for half the length of the chord joining the endpoints of the arc of the circle. Okay? So this is the Samastaja, and half of it is just Ja. The term Kotija, often abbreviated in Indian texts as Koja, means the side of a right-angled triangle, one of whose sides is the Ja. So here is a right triangle formed by this half chord or Ja, and this portion of the radius coming from the center to that chord, which they call the Koja. So Koja and Ja, and this would have been the hypotenuse or the radius. There's the right triangle. Indian astronomers use the value of R to be 3.43 or 3,438 to represent the distance from the Earth to the sun, because this is roughly the radius of a circle whose circumference is 360 degrees, which is 360 times 60 feet, or 21,600 feet measured in, oh, it's minutes. Okay, sorry, 360 times 60 minutes, or 21,600 minutes measured in minutes. Okay. So before I get to this, okay, so now it has exercises 1 through 3 in the teacher edition, but not in the student edition. And it says in his text, Ariabata constructed a table of values of the Ja in increments of 3 3/4 degrees, which were used to calculate the positions of the astronomical objects. The recursive formula he used to construct this table is as follows. S sub 1, in other words, the first term, we start at 225. Okay, and then S sub n plus 1, or the second term, is equal to the S sub n plus S sub 1, which is the first term, minus S sub 1 plus S sub 2 all the way out to S sub n, all divided by S sub 1, which is the first term. When n counts the increments of 3 3/4 degrees, then Ja is the point n times 3 degrees, which equals S of n. Okay, so that's where this comes from. All right. So what they're saying is where n counts the increments of 3 3/4 degrees, then Ja is n times 3 degrees, which equals S sub n. So from there, we're going to start. Let me just shrink this a little bit so we can see the top. So now what are they asking us to do? It says calculate Ja 7 degrees, 11 degrees, 15 degrees, and 18 degrees using Ariabata's formula. Round to the nearest integer and add your results to the table below. Leave the rightmost column blank for now. Okay, so they gave us the first term. N equaling 1 is S sub 1, and that starts at 225 degrees. Okay, so that is right here. That's where that came from. Okay, so what we need to do now is fill in this table. Okay, so doing this sequence, keep in mind, S sub 1 is 225. S sub n plus 1 equals this formula here. So we're just going to do this formula again, over and over again. So if I were to do this to calculate 2, 3, 4, 5, which are blank, I would use this formula here. And so if I substitute in n as 2, if n is 2, then it would be S sub n plus 1. Okay, so if I have S sub 2, and that equals S sub something plus 1, well, what is that n? It is 1. 1 plus 1 is 2, so my n in this case is 1. So it's S sub 1 plus 1. So that's going to equal the formula S sub 1 plus S sub 1. Okay, so I'll just write it the first time. S sub 1 plus S sub 1 minus, in parentheses, S sub 1 plus S sub 2 divided by S sub 1. So S sub 2 is going to equal, well, what is S sub 1? S sub 1 is 225. Plus S sub 1 again, 225. Minus, okay, now actually we're trying to find S sub 2. So this is also S sub 1 right here. Okay, because that's our S sub n. S sub n is S sub 1, so it's going to be, in parentheses, 225 plus 225 divided by S sub 1. Okay, so S sub 2 is going to equal 225 plus 225 is 450. Minus 225 plus 225 is 450 divided by 225. So that S sub 2 is going to equal 450 minus, and 450 divided by 225 is 2. So S sub 2 is going to equal 448. So this would be 448. Now the teacher's edition says it's 449, and I'm not certain how they came up with that, but I come up with 448, so that's what I'm going to use. And then we would continue doing this. So that's the process. So now let me get rid of this formula here. And now answer this question, exercises 1 through 4. So it says to calculate jaw 7 degrees. Okay, where theta in degrees, jaw 11 degrees, 15, and 18. All right, so jaw 7 degrees, 11 degrees, 15, and 18. So these are approximations. They want us to do these. So we're going to continue with this formula. So now I keep that 448, and now I'm going to use it in this formula. So let me just erase all of this. And we're using this formula here, but now it's going to be S sub 3. Whoops. Trying to get my small eraser here. And this number is going to change each time. All right, and actually so is this one. Okay, so the formula says, now we're going to do S sub 3. So S sub 3 equals some S sub n plus 1. Well, that n is going to be 2. So what we're going to do is we're going to take S sub, and what was the formula? S sub n, which is, my n is 2 this time, plus 1, S sub 1 minus S sub 1 plus S sub n, which is 2, divided by S sub 1. So S sub 3 is going to equal S sub 2, which is 448, plus S sub 1, which was 225, minus S sub 1, plus S sub 2, divided by S sub 1. So S sub 3 is going to equal 8 and 5 is 13, 4 plus 2 is 6, plus 1 is 7, and 4 plus 2 is 6. So, oops, not equals, minus minus, and then notice that we're adding the same thing here. So it's just going to be 673 divided by 225. So S sub 3 is going to equal 673 minus, and then I go to my calculator, and I'm going to put 673 divided by 225 and hit enter, and that's going to be 2.99 or 3. So S sub 3, because it said to round to the nearest integer, would be 670. So this would come out 670. So there's our S sub 3, which is JA 11. Okay, now I'm going to get rid of this. Okay, now we're going to do S sub 4, which is going to be S sub 3 plus 1. Let me just get rid of this here. So according to the formula, it is, so now we're doing S sub 4 now, which is S sub 3 plus S sub 1. So S sub 4 is S sub 3 plus 1. So it's S sub 3 plus S sub 1 minus S sub 1 plus S sub 2 plus S sub n, which is 3. All divided by S sub 1. That should be S sub 3. So S sub 4 is going to equal S sub 3, 670, plus S sub 1, minus S sub 1, minus S sub 1, which is 225, plus S sub 2, which is 448, plus S sub 3, which is 670, which is our S sub n. So that's where we stop, divided by 225. So S sub 4 is going to equal 5 plus 0, 2 plus 7, 2 plus 6, plus, not plus, minus the quantity 225, 448, and 670. So 225 plus 448 plus 670 is 1,343. And that's going to get divided by 225. So S sub 4 is going to equal 895 minus, let me do this, hit that by mistake. So 1,343 divided by 225 is 5.96, which is about 6. So I'll just write 6. So S sub 4 is 889. Okay, and each one of these is off by 1. The book, the teacher edition says 890, 671, 449. Okay, but I'm just going to keep doing it this way. I'm not sure why it's off by 1, but it is. Okay, so now we're going to do S sub 5. Let me erase all this. Okay, so S sub 5 is sum n plus 1. So it's obviously 4 plus 1 gives us 5. So it's going to be S sub 4 plus S sub 1 minus S sub 1 plus S sub 2 plus S sub 3 plus S sub n, which is 4, divided by S sub 1. Okay, so S sub 5 is going to equal S sub 4, 889, plus S sub 1 minus S sub 1 plus S sub 2 plus S sub 3 plus S sub n, divided by S sub 1. Okay, so S sub 5 is going to equal 9 and 5 is 14, carry the 1, 8, 9, 10, 11, carry the 1, 8, 9, 10, 1,114, minus, and then I go to my calculator, and it is 225 plus 448 plus 670 plus 889. And that comes out to be 2,232. And we divide that by S sub 1. So S sub 5 is going to equal 1,114 minus, and now I just hit divided by 225, and I get 9.92. Okay, so 1,114 minus 9.92 equals 1,104. So S sub 5 equals 1,104. Okay, and the teacher edition says 1105. So I'm off by 1 on each one, but according to my calculation, that's what this is. Okay, so we just answered this question. We calculated jaw 7, 11, 15, and 18. We rounded to the nearest integer and added our results to the table below. It says to leave the rightmost column blank for now. So that's all they wanted us to do here. So we are done. Okay, page 4 brings us to number 2. And in this one, it says label the angle theta. So let's do that. So here's our angle. So this is theta degrees. Okay, so there's the angle theta. It says to label jaw theta. So let me do that in green. Okay, right here. And that's a little bit thick. Let me thin that a little. That's good right there. So there's, and it's not all the way down. Okay, so there is jaw. That's jaw. J-Y-A. What was that? So there's jaw. And koja is going to be the distance. Let's make it this. Okay, actually, I want a line segment, medium, and blue. Okay, so right there is koja. All right, so this is definitely a right triangle because jaw is perpendicular to koja. And it says label the angle theta right here, jaw, koja, and r. So r is the radius of this circle, which is the distance from the center of the earth to the center of the sun. Okay, so there it is, all labeled in the diagram. Now part A says, how does this relate to something you have done before? Okay, well, jaw and koja are lengths of the sides of a right triangle. They're also like the height and co-height functions of the passenger car on a Ferris wheel in prior lesson. Part B, how do jaw theta and koja theta relate to lengths we already know? Okay, and here's where it comes together. From prior work with triangle trigonometry last year, jaw theta equals r times the sine of theta. So let's do a quick review on that. Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. And tangent equals opposite over adjacent. So if we're talking about the sine of theta, so if I want to know what the sine of theta is, that's the sine of this angle here. It's opposite over hypotenuse. Well, that is jaw divided by r. And in order to get rid of this r, I multiply both sides by r, and the r's cancel, and that's where I get r sine theta equals, there should be an equals there, jaw. So jaw theta equals r sine theta, and koja equals r cosine theta. So again, if I were to do that, cosine is adjacent over hypotenuse, which is koja, over hypotenuse, which is r. Multiply both sides by r, and we would get r cosine theta equals cojut theta. And r cosine theta equals cojut theta is right there. Okay, so there's a review from algebra or geometry last year. And number 3 says, use your calculator to compute r sine theta for each value of theta in the table from exercise 1, where r is 3,438. Record this in the blank column on the right in exercise 1, rounding to the nearest integer. How do Ariabata's approximated values from around the year 500 CE compare to the value we can calculate with our modern technology? Okay, so let's go back to that and we're going to calculate it. Okay, so R is 3,438 and we're going to compute r sine theta for each value of theta in the table. So if I come back to this table, okay, sine theta is this. Now let's look at this here. Ja theta equals r times sine theta. So if I go back, ja theta is right here, and that should equal r sine theta. Okay, so if I get my calculator out, okay, so here's the calculator. So what do I want to put in? I want to put in r sine theta. Well, here is our theta in degrees. So for this calculation of the first one, I would do, and here's what I'm going to do instead of typing in 3438 every time. I'm going to store that as r. Okay, so now that's r. So I'm just going to put alpha r times the sine of this degree measure, which is 3.75, 3 3/4. 3 3/4 is 3.75, and I hit enter, and I got 224.85. All right, so that would go here. And did it say to round? I believe it did. So let's go back. Part 3. Okay, record in the blank column on the right, rounding to the nearest integer. So I don't want the decimal. So that rounded to 224.8 rounds to 225. 225. Okay, and we're going to keep doing that. So now it's going to be alpha r times the sine of 7.5. And I got 448.7. That rounds to 449. So I might have done something wrong in this calculation. I am off by 1. Okay, so that's really close. Okay, so then we're going to do alpha r sine 11.25. Whoops, what happened here? Clear. Alpha r sine 11.25. Enter. And I got 670.7, which is 671. Okay, and we keep going. Alpha r sine 18.75. No, just 15, around 15. Okay, and that will give us 889.8, which comes out to be 890. All right, and finally, alpha r sine 18.75, and I get 1105. Okay, so these calculations, this one was correct. I'm off by 1 here, off by 1, off by 1, off by 1. And in the book, it did show these values, but I'm still thinking that this calculation over here is correct to get these numbers. We're only off by 1. Okay, so it's pretty close. So now let's go back. And part 3 says, how do Ariabata, thank you. How do Ariabata's approximated values from around the year 500 CE compare to the values using modern technology? And the answer answer to that is the values are surprisingly close. Okay, page 5, I'm just going to say a little discussion here, talk about this here, where did sine come from? So if we set the radius to equal 1, then ja alpha degrees equals the sine of alpha degrees. And koja alpha equals cosine of alpha. So Ariabata constructed the first known sine table in mathematics. This table was used to calculate the positions of the planets, the stars, and the sun in the sky. If the first instance of the function we know now has the sine function started off with the Sanskrit named ja, how did it get to be called sine? Okay, so here is where sine came from. We know Ariabata referred to this length as ja. Transcribed letter by letter into Arabic in the 10th century, ja became jiba. In medieval writing, scribes regularly omitted vowels to save time, space, and resources. So Arabic scribes wrote just JB. Since jiba isn't a real word in Arabic, later readings interpreted JB as jaib, J-A-I-B, which is an Arabic word meaning cove or bay. When translated into Latin around 1150, jabe became sinus, which is the Latin verb or Latin word for bay. Sinus got shortened into sine in English. So there you have it. That's where the word sine came from. Okay. And then we even shorten it even more. We don't put the E at the end. We call it S-I-N or just S-I-N, and it's still pronounced sine. So number 4, we will assume that the sun rises at 6 a.m., is directly overhead at noon, and sets at 6 p.m. We measure the height of the sun by finding its vertical distance, ja, from the horizontal line. The horizontal line that connects the easternmost point where the sun rises to the westernmost point where the sun sets. Using R equals 3,438, as Ariabata did, find the height of the sun at the times listed in the following table. Okay, so if the sun is rising, keep in mind, let me bring that diagram back in from the first page. Here's the diagram. So let's just keep in mind that what's going on here. At 6 a.m. is where the sun rises. That's what we're told. Well, at 6 a.m., we are right here, and the angle measure right there is 0 degrees. At 12 p.m. is at high noon. That is right here. Well, that is 90 degrees. So if I am going to determine, okay, if we have 6 here, and then we have 7 here, 8 here, 9 here, 10 here, 11 here, and 12 here, this would be 45 degrees. Okay, we're halfway. So 9 a.m. is 45 degrees. And so from 0 to 45 divided by 3 is 15-degree increments. So this would be 15 degrees, 30 degrees, 45, 60 degrees, 75 degrees, and 90 degrees. Okay, so those are the values we're going to use. So we're going to do the degrees as ja, 15 degrees. Ja, 0 degrees, and so on. All right, so we're going to calculate those. So remember, ja is the same as r sine. So sine of 0 is 0. So the height of the sun is 0 degrees, or 0 feet in this case. Okay. So we're looking for the heights. We're trying to find the heights, which is just ja 0, ja 15, ja 30, ja 45, all the way up to 90. So then if I do sine 15, I get 0.25. Okay, but what you have to remember is that we are using r, which is 3438. So I need to do r times the sine of these. So if I go back, remember I've already put r in as r. Why did that not use alpha r? And now if I do sine 0, well, 0 times r is still 0. But if I do alpha r times the sine of 15, I'm going to get 889.8, and we're going to round. That is 890 feet. Okay, so in 1 hour later, the height of the sun above the horizon is 890. And if I keep doing this, I'm going to find where the sun is in every 15-minute increment. So then I'm going to do r sine 30, and that is 1,719 feet. So that's 1719. And then at 9 a.m. is at 45 degrees. So alpha r sine 45 is 2,431. Okay. And then after that, we're going to do r sine 60, alpha r sine 60. And that is going to be 2,977. And then alpha r sine 75 is going to put us at 3,321. And then at 12 noon, it's going to be alpha r sine 90. And that gives us 3,000, and that's our radius, 3438. Okay, and that's our r, because the sine of 90 is 1. Okay. Saying feet. This height is not in feet. It was just what the Indians used back in the day to determine the height. They used 3,438 for their distance from the center of the earth to the center of the sun. That's just the number they use because of the 360 degrees. So part B says, now find the height of the sun at the times listed in the following table using the actual distance from the earth to the sun, which is 93 million miles. Okay, so this 3,438, think of that as a unit circle, r equaling 1. So if we just multiply these by 93, that'll tell us how many millions of miles high the sun is from the horizon. So 93 times 0. So I'll write it the first time. So what we are actually doing is taking 93 times that ja 0 divided by 3,438. So we're taking this divided by 3438. Okay, because if we take this 3438 divided by 3438, we're going to get 1. Okay, and that'll give us the 93 million miles it is away when it's at its highest point in the sky. So if I just multiply all these values basically by 93, will that give me the right value? So if I take 890 times 93, that's 82,770. So then if I divide that by that 3438, okay, that will give me 24.07, or rounding that to 24.1. So this is 24.1. This was 0. And it says, okay, it doesn't say, but I'll do it in tenths. So if we keep doing that, so really what we're doing is we're taking these values here, dividing by 3438 and multiplying by 93. So 1719 divided by my r, if you will, I can use that r, and I get 0.5 times 93, and that is going to give me 46.5. Okay, so next one, 2431 divided by our r will give us 0.7 times 93 will give us the miles, millions of miles in the sky, 65.8 in this case. Million miles up, okay? And then at 10 a.m., we're going to take 2977 divided by our r. Oops. And that is going to give us 0.8659 times 93 million miles will give us 80 million, 0.5 or 80.52, so it stays 5. Okay, so number 11, 3321. 3321 divided by my r times 93 is 89.8 million miles from the horizon. Okay, so there are the values when we use the estimation of 93 million miles away. All right, page 6 brings us to the end of lesson 3. Review the lesson summary and go to your problem set.